Welcome to the first question of the day. What does this question say? Prove that there exists no square ABCD with A and B on y is equal to Bx and C and D on y is equal to ln x. I'll give you 5 seconds to pause the video and try the question yourself. 5, 4, 3, 2, let's go. Question is from AOPS. I'll link to the original question down in the description. Let's see what the question says. We have two functions given, e raised to x and ln x. Now, e raised to x and ln x are what are called inverse functions. What are inverse functions? Inverse functions are functions which are defined as such that if e raised to a is equal to b, let's say, then ln b will be equal to a. This is what inverse functions are. So, if a comma b is on a comma b is here, then b comma a will be here. This is what we mean when we talk about inverse functions. A comma b is in e raised to x, then b comma a will be in ln x. This is what we mean when we refer to such functions. That means that they will become symmetrical about a very fine line known as y is equal to x. This makes the graph part of the question. This relates these functions well enough. The second part, what we want to do is a geometrical thing. What I am going to claim is, let's say I have a trapezium. If I have an isosceles trapezium and I am able to get this above side, let's call the side AB, and I am able to get CD. If I am able to somehow get AB is equal to CD, then congratulations, I'll have a rectangle. Right? I'll have a rectangle. Now what we are going to prove is that getting a rectangle is also not very much possible over here. That is what we are going to prove. Go about it. We will take in point A and B on Ex and C and D on ln x, and we will get C and D by reflecting A about y is equal to x and B about y is equal to x. That's how I am going to get those points. So I will take A as an arbitrary point A comma A, and I will take B as B comma EB. As I am reflecting about y is equal to x, I will say C is E comma B, and D is E comma A comma A. Right? These are the facts of this matter. Now, what do I need to do? I need to get AD equal to BC. That's what I need to get. And if I want to get AD equal to BC, what will I do? I'll just pick my nice pen and I'll put a different formula right here. What is the different formula here? A minus EA whole square plus EA minus A whole square. This is the distance AD. What is the distance BD? Sorry, BC? B minus EB whole square plus EB minus B whole square. Now notice that A cannot be equal to B. As a fact of the question, we will not put A equal to B ever, because that will just give us a straight line somewhere. A is equal to B, this is a straight line. Obviously, that is not a square or a rectangle actually. So it's not a proper square or rectangle, so we will not talk about it. Let's come back here. What will I do? I'll cancel these both out. Right? Square roots can be cancelled. Next, I'll notice A minus EA is equal to A minus EA whole square is equal to EA minus A whole square. So this will turn into 2 times A minus EA whole square is equal to 2 times B minus EB whole square. As you might notice, we can cancel the 2, we can cancel the square. When we cancel a square, we need to write a plus minus, right? So we will write a plus minus A minus EA is equal to B minus EB. Right? These are some more facts which we are able to generate. Plus minus. Now if I look at the plus case, it is A minus EA is equal to B minus EB, which will imply that A is equal to B, because these are both increasing functions these are both decreasing functions by the matter of it. So no, plus case does not really work. If I go for the minus case, what am I left with? EA minus A is equal to b minus eb, right? This function is strictly increasing in one range, this function is strictly decreasing in another, in the same range, right? Which means they will only meet once. They will at most meet once. As you might notice, they don't. This graph is for e raised to x minus x, and this graph is for x minus e raised to x. As you might notice, there is no particular value where these both meet, which means there is no there exists no pair AB such that this is true, and hence there exists no square AB.